So this is a workshop about avalanches, and so you can see that we have a few places here where we can actually see avalanches on the field. That will be the only relation between my talk and avalanches, I'm afraid. But not maybe the other. So let me first start by thanking the people with whom I have been working with on this topic recently, and especially Kirsten Martens, who was attending the conference last week or the week before last, Alexandre Nicolas, who just finished his PhD on the topic, and Lideric Bocquet, with whom I have been collaborating for many years on this topic, and others. So I will start with a very short introduction to the deformation of amorphous materials. This has been already discussed by many people in the workshop. So let me just briefly recall that the kind of quantities we are interested in may be flow curves, so the stress as a function of the strain rate for an amorphous material, which typically looks like shown here, with a yield stress and a Poirot behavior when the stress exceeds, as a function of strain rate, when the stress is exceeding the yield stress. So the reference behavior would be the Newtonian fluid, this log-log curve. And very often the behavior of amorphous solids is described by the so-called Herschel-Bulkley equation, which has this Poirot here, which is actually, which probably shouldn't be interpreted as describing something critical, but rather some effective fit over a broad range of strain rates here. This is real data from a microemulsion. So you see this Herschel-Bulkley law here in log-log, and you also see it in lin plot. Sometimes people have get the impression that this is a very weak variation as a function of strain rate. Actually, if you plot it in linear coordinates, you see that the variation as a function of strain rate is quite fast.
It's real data, so it's fuzzy, right?
So no, it's pasted from a cut and paste from a PDF, but the real data is quite accurate, I hope. That's also real data, but now for stress strain curves. So you apply a strain at some fixed rate and temperature. That's for a bulk metallic glass, and that's for a again for some kind of colloidal paste, not a microemulsion. So you start with an elastic behavior. You have a stress overshoot in general, and then you go into the plastic deformation regime here, which can be held steadily in a rheometer for a colloidal paste. For a metallic glass, generally the system will break after some strain localization has taken place.
Excuse me,
yes.
Did you say what the exponent alpha is typically? On
the previous slide, so typically the exponents alpha are thought to be in the range between 0.5 and 0.7, I would say. So 0.5 is a typical value, but effectively, depending on the range of strain rates that you are using to fit, you may find different values.
So it's less than unity?
Sorry?
It's less than unity?
It's less than unity, yes. So this is why the curve is, so in linear, the curve starts with a vertical tangent.
And are there theoretical predictions for that? Or?
I'm sorry?
Are there theoretical predictions for alpha?
I'll come to that. Yeah. So that's the stress strain curve, and you see, so yesterday or the day before there was a question about the values of the yield strains, and you see that the yield strains here where the peak is located are indeed typically between 5 and 10% here.
And in the second plot, this is a function with the aging of the system.
Yes, so the yield stress, the peak increases, the overshoot increases with aging. That's very classical. And of course, this is a log scale. So this is just the elastic regime, but it looks exponential instead of linear.
Do we have any reason to believe that after those overshoots, the flow is homogeneous, or?
Here, certainly not. You should ask Conrad, but very very likely you have strain localization that is taking place here where you have these oscillations. And then
Well, that oscillation, I was told by none other than Johnson or one of his collaborators, was just an instrumental error.
what's that?
Instrumental error.
No, he means this jerky flow.
No, that's not it. Look, I mean, see, you see that curve that does.
This oscillation.
That's nothing.
It's not, so it's not. It's good.
But that's in the regime where the derivative of the stress strain curve is negative, it's intrinsically unstable there, right?
Yes. So if you will accelerate if you apply a
No,
final.
depends on the driving condition.
Yeah.
No, it's not necessarily unstable.
Depends on how you drive it.
It depends on the driving, yes.
Yeah. But it's,
And in the colloidal system, I believe that you can check here that you can sustain a homogeneous flow for this specific
Even
system.
in the regime with a...
Well, I mean, this is a transient, and when you get into the kind of plastic flow regime, then it's homogeneous.
and
Here.
if you had that as in the stress strain rate curve, then you would decide that there was
Oh, yes.
something to go with. But this is the stress strain curve and it's at a fixed strain rate. So it's
Oh,
So-
you're
so-
fixing the strain rate. Okay, I see. Sorry. Okay.
Yeah, yes. What is unstable is
Right.
if you have
Right,
sigma
right.
as a function of gamma dot,
Right.
and then you get something like that. That part is
Right, but this is fixed strain rate. Okay.
yeah.
From presuming machine like strain control. Right?
Okay, so now if you look more closely on the microscopic samples, and nowadays, so this is relatively old data that was taken on the foam, in which you have very few elements in the system, in the sense, but nowadays people like Conrad are getting similar data for metallic glasses on very small nanoscale samples. Then you see that you have this kind of very jerky behavior, actually, which for large systems gives something that looks smooth. Okay, and this tells you that the deformation proceeds to rather well identified plastic events, so-called, that correspond to the stress drops on these curves. So sometimes you have small stress drops, and sometimes you have large drops, which corresponds to lots of plastic events that are taking place more or less simultaneously. And it's also now, I believe, quite well documented from experiments, and that's also something that Jörg showed you on Monday from simulations that we have seen in a number of talks in the last 3 weeks, that these events are basically, the most elementary event is basically a shear transformation of the Eshelby type. And this was seen early on in experiments that would look at a single experiment or simulation that would look at a single event and look at the stress field or the strain field around this single plastic event. But nowadays people have more and more characterized this Eshelby-like.
So what does Eshelby-like mean?
Eshelby-like means that, I will again come to that a bit later, but it means that basically you have one part of the system that becomes, you have basically a spherical inclusion that is replaced by a liquid. And so the spherical inclusion will progressively deform into an ellipsoid.
Okay.
Okay. And so the result of that is that you have quadrupolar looking in terms of symmetry and dipolar in terms of distance dependence correlations between the events. So this is shown in a very recent paper by Weitz, Speppen, and Jensen, in which they strain a colloidal glass again. So this is basically a picture of the displacement of the particle. So they do a cyclic experiment. This is a picture of the strain, of the plastic strain, in fact, that is observed. So it looks, after a complete cycle, it's very disordered. But now if you look at the correlation, the spatial correlation of this plastic strain, you obtain quite clearly the quadrupole distribution that you see here. Okay.
So this is the individual events you're saying also look like these Eshelby things, because that's a correlation function of many events.
Well, that's the correlation function of the pattern of many events. But the implication of this is that every single event is correlated with subsequent events that it has triggered through this kind of propagator.
But just to be clear, we should think of this as being way up somewhere on the flow curve, not necessarily near the yield stress, right?
It's a good. I'm not sure. I mean, you can probably read off the strain. I mean, this is a cyclic thing, and I'm not sure what the maximum strain they went up to is. It's probably like, I would say from this, it's, yes, probably more than 10%, so it's beyond the yield.
No, but I mean the rate effects, right? So we shouldn't think of this as being something that you would see if you're driving the system quasi-statically. Or
Yes, this is very slow. This is quasi-static.
Well,
Or it's slow.
It's an experiment.
It's an experiment.
On a colloidal, but it's not done at a high temperature or at its high strain rate. So it's a very controlled experiment. You really can see what's going on. It's nice.
Do you know what the strain rate was?
I can, but it was slower, I'm sure. And what is quite interesting, in fact, is that they also looked at the same system under quiescent conditions, so no applied strain at all. Okay, so they just look at the system during aging, and during aging, they also see events that accumulate, and in the end, it's less clear than in the strain case, but they also see kind of quadrupolar correlations. The point is, yes.
What is on the axis of this thing?
That's probably.
Rate of correlation.
There's more resolution.
Yeah. So this is just a distance from the event. I mean, it's a space correlation function. Okay, so micrometers here. I'm not sure what exactly the size of the particles is, but it's probably slightly below 1 micrometer.
This is essentially a two-dimensional system, is it? It's a layer?
No, it's a slice of a 3D system.
Oh, I see.
It's a
Okay.
colloid?
Sorry?
It's a colloidal?
Yeah.
Yes, it's a colloidal. Yes, okay, so this means that even in the system which is not under stress, you have the same type of events that are taking place. And here, I don't go into the detail, but what the correlation function they look at is calculated in a way that highlights the fact that you have directional correlation, because, of course, in a quiescent system, you wouldn't expect anything to be directional in a sense.
But it's a high enough temperature so that it's not completely stopped.
Exactly. There is some aging, but still so it's in a regime in which the sea, it's quite solid. They can strain it slowly, but there is still some activity, and you see that the activity during aging is of the same nature as the one. So that's something similar for a foam now. These are experiments by Eric Weeks, and in the foam you can actually kind of measure the stresses optically because you know exactly what the forces that are exerted are. And so here, this is a geometry in which the foam is actually flowing and subjected to a simple shear. I mean, the place where the images are recorded are in a simple shear geometry. And pure shear geometry, sorry.
Can you just make, the color is indicating what? What the plot is of what quantity?
Okay, so at the center that's where you identify what is called a T1 event in a foam. And the color plot is telling you how much the stress is changing away from the central
But it's one
event.
component of the stress you're looking at.
The component you are looking at is the shear stress, so the shear sigma, the shear component of the stress tensor in 2D.
The magnitude of the shear.
The magnitude of the shear. Okay. And so again, you see the same kind of pattern. It's typically what they did is to fit that with a quadrupolar form, but they also need to add some isotropic term, which could indicate that there is some dilation, but that's not clear where the isotropic term is coming from. Okay, and then on granular system,
One question there. How is it? So it's the theory. Which one is the theory? That one.
That one.
And that didn't depend on the packing fraction?
No, the theory is just a plot of the Eshelby propagator with the same color code as here. That's it.
And sorry, why are there multiple plots of the same volume fraction?
I'm sorry?
There are multiple plots of the same volume fraction.
Maybe that's a typo. Maybe it should be 9-2.
Yeah, but
9-1, 9-2,
9696.
Typo.
Yes, it looks like that's something.
What kind of theory did they use? What kind of theory?
This is what they call theory here is just a representation of the Eshelby propagator. Yeah. Okay, so now next thing in granular media. So sometimes people believe that granular media behave completely differently from classical mechanics. But in fact, it is a very nice experiment by Le Bouil, Crassou, and Amo. They did also identify in the...
Can we just clear up what's being plotted? So the stress tensor is a tensor, and it's being dotted into the direction between the 2 points, something like that?
no.
The stress tensor in 2D will have one component which is associated with the pressure, basically, and one which is the stress
No,
component.
it has two associated.
Okay.
There's still two associated with it.
It's a sine quantity.
What?
It's a sine quantity. The shear is in one sense and along the 45-degree lines and along the...
Right, but that's why you have to take the 2 points, look at the distance between them, and it's that you need that and the stress tensor, right, to get a scalar quantity out.
He's not really plotting a scale.
He's not plotting the scale.
The color is a scalar quantity.
I think,
Yeah.
he's plotting a scalar. He's plotting one component of the strain tensor, which doesn't transform like a scalar under rotations, but is a scalar.
No, he's plotting, if you take the distance between 2 points, then you can make a scalar out of that and the stress tensor.
Yeah,
That's what I suspect that's what he's plotting. That's what gives you the four-fold symmetry.
No.
Yes, this is under no stress, it's under no load. So where are you getting, what's giving you the action?
Yes, there is.
He's taking the XY component of the tensor.
I mean, this is a
Plotting it
What?
in X.
Is it the response to unit shear in the center?
this is a form. This is a form which is being strained. So there is a direction.
Even in the relaxation plots he was plotting before, he mentioned without stressing it, without emphasizing it, that it was under stress to break the symmetry, otherwise you couldn't see it.
No, Jim, I don't think that's right.
What?
Sorry, not to confuse things, but so
Oh,
in the quiescent state, he's picking some particular Cartesian component. He's picking
Yeah,
the YZ component. And
exactly.
showing the correlations in the YZ plane. That's
thank you.
what breaks.
Right, but
I'm sorry, thank you.
Right, so he's picking up, it is
Picking up an
So he's picking out one component.
you can put the components together and still get the structure if you, okay.
But basically, if you have a shear transformation in
No, I
some
understand
place,
what's happening, I just don't understand what's being plotted.
then it's one component. It's let's say sigma x minus sigma y.
Okay.
Or the variation of that. And so here, the same thing is shown for a granular medium that is under uniaxial compression. So at the beginning of the compression, you observe the plastic activity is observed by looking at some diffusive waves spectroscopy intensity. So the spots here, the brown spots, correspond to places where you have high plastic intensity. And again, when you look at the correlation between two such images, at the correlation function of such an image, then you get something that has the same type of symmetry. So even in the granular medium, it seems to be that you have the same type of elastic events that are taking place, and that eventually, after a large deformation, organize into shear bands that are shown here, that are really macroscopic shear bands. So here you wouldn't pick up any particular direction by eye, but if you look at the correlation function, the space correlation function of the image, again you pick up the particular directions that are associated with the Eshelby transformations.
We had a lot of discussion of this. Is this a surprise? It would seem very natural. But
well,
it's an elastic dipole and it
Right.
rearranges, and I would see correlations.
As long as it's rough, it's pseudo-linear.
Well, to many
It's
people,
like your elastic theory.
yes,
Right.
but I don't know, to many people in the granular media or the soil mechanics community, it's not obvious that you can apply elasticity to granular media. And
Good.
in
Good.
fact,
But if you're not confused about that, then it's,
well, but many people, that's a very strong belief in this community.
Yeah.
And then the interesting point is that the shear bands here are actually occurring at an angle which is different from the correlation that you see here.
No, shear bands,
But
their formation is much more deep.
Yes, that's. But it's a very interesting issue because these are real granular media. There is friction, there is everything, and the shear bands are taking place at an angle which is associated with friction.
At a, what was the word?
With friction, the angle is given by the Moore criterion, basically.
Angle.
Yeah.
Thank you.
Okay. And so it's very interesting it would be very interesting to understand how how you go from a purely elastic system to something which has somehow friction in it. That's
Jean-Louis, so from the image on the left, I don't know that Eshelby.
from the image here.
Yeah, I don't
No.
know Eshelby until I do some detail.
Until you do the correlations.
So in C, that's one example, but they're saying that every one of those spots looks like C.
No, that's the correlation.
That's the correlation
Between
pattern.
the spots.
That's
So-
for one spot.
No, that's the correlation of the image. So you do the spatial correlation function of the image, basically.
So John, I guess I don't understand the significance of it being Eshelby or not. I mean, these correlations will be there. Any local transformation which has a shear, nonlinear thing will give you this. So what? There's a particular one if you look at it on small scales.
Yeah. Eshelby was old enough that he was the first to figure out what the dipole field looked like.
Yes, it's like
People
Really?
wanted that for Eshelby.
it's like if I say 1 over r, I would say Coulomb.
Oh,
If I say,
Isn't Eshelby still?
He's probably not the first. He's the first in this field. One of those things.
Okay, I see. Okay.
Okay, so a few features of the flow of amorphous solids that connect to statistical physics and what is studied in this workshop. So these statistical aspects, possibly the interplay with aging, the fact that maybe if you want to, you can rewrite the Herschel-Berkeley law to make it look like a critical law, and things that seem to be quite universal, going from granular media to metallic glasses. So this suggests to develop simple models, and the simplest models that kind of encompass the features that have been shown from the experiments and the simulations are what I will describe as mesoscopic elastoplastic models. And the first to develop these kind of things were probably Bulatov and Argonne about now maybe 20 years ago. And they were followed by a number of others, so Damien has presented some of that also. The basic idea is that you want to coarse grain your real system into zones or region of space. And that you want to describe the basic mechanism by which a region of space under stress will yield at some point, and the stress that it was supporting will be transmitted to the other regions of space. And this is what is the Eshelby thing. And then, after yielding, then this specific region of space becomes elastic again, etc. And that's how the flow proceeds.
And what's the procedure to set the scale of the first game?
That's a good question. It would be basically to try to fit, and I will show that in the last part, but basically trying to fit some flow profile to experiments. Typically what you expect from the simulation data, for example, is that these regions would be typically 5, maybe 10 particles across.
And it could become much larger if you approach the transition like...
If you approach jamming and, or unjamming rather, then they could become larger, yes. So more precisely, how does one describe the local thing? Well, you start with an incompressible elastic medium. It yields, or which I will describe yielding, basically to me would say that it becomes like a fluid, so it's not able to sustain any elastic stress within some region, which will be the plastic inclusion in the Eshelby sense. And so inside the plastic inclusion, the elastic force that was on the boundaries is not supported anymore by the elasticity of the region, but by some dissipative mechanism that in the simplest description you could describe as a simple viscosity. Okay? And then the plastic strain in the inclusion will increase with time, and as a result, the boundary of the inclusion will be deformed, and the stress and this deformation on the boundary will induce stresses in the rest of the material.
I understand that you may not want to have a stress which is linear in the strain because you said it's a fluid, but could there be non-linear terms?
There could be. I mean, the only point I would
single out the dissipative part to be the relevant one rather than say some non-linear terms in the strain.
Let me ask you an even broader question. All of this can be thought of as the multipole series. This is the leading term in elastic theory, the multipole series.
Yeah, that's a far field.
Who cares what the individual microscopic mechanism is?
Right.
The
idea that it's melting in the spherical region,
okay.
becoming an ellipsoid.
No, there are two. You are making, I believe, two very different points. Your point is we only care about the far field for the elastic part, which says I agree. Maybe quantitatively you may want to worry about, but okay. Let's say we only worry about the
far field may never be reached if you're close to the transition, where the blob becomes a
yes, of course.
But what Vincenzo was saying is, I believe, something different. It's about the dissipation mechanism inside the region, and this dissipation mechanism is important if you want to go beyond quasi-static things. In the quasi-static things, you assume that the region relaxes completely, and you start over again. Now, if you are driving your system at a finite strain rate, this is not what is happening. You actually relax the stress inside the region on some time scale, and this time scale is essentially what will govern the deviation of the flow curve when you have the deviation. The fact that the stress increases as a function of strain rate, this will depend on the mechanism inside the inclusion.
No evidence that the elastic that the Eshelby long-range fields, the elastic multipole, dipole, or quadrupole fields, that's got good experimental evidence. Is there any evidence that the dissipative mechanism in here is responsible for the rising gamma dot? Is there any direct connection there?
Well, perhaps in forms, but no, I don't think there's any direct evidence from experiment.
Good. Okay.
Perhaps from forms there are some, I mean, in forms you could think of varying the viscosity of the liquid and see how this changes the flow curve. But I don't think this has been done in a systematic manner. But still, I mean, I think we all agree that it has to be like that. That
Can we let presenting a model that has some purpose, because it's going to give you the interplay between these different time scales, as he's already discussed it. And it's a model that obviously has phenomenological features to it, and the interesting question is, does it solve some of the interesting problems that a number of us have been concerned about? So I think we should, I want to hear how he does it.
Okay, but I agree there's no clear, I mean, that's just the simplest assumption.
It's very important for keeping attention.
Yeah, but as long as we let the speaker get to what he wants to tell us.
Okay, so now the stress is transmitted according to this propagator that has this fourfold symmetry and the dimension of space here. So this is something everything agrees about. If you have, for example, walls, then you have to modify this slightly, use images, etc., to get a modified propagator. But that's not very complicated. And so what I want to do now is two things. The first thing will be, what I would like to do is kind of recap the mid-field approaches or mid-fieldish approaches that have been used to describe this kind of elastoplastic mechanism. And the second thing is to show you some results on a specific example of how these lattice models can be actually implemented and reproduce some features of seen in experiments. So the part on the mid-field model, I just wanted to do rather on the blackboard because it's yes. So this will be a very short summary of 3 different papers. So the first one is a PRL of 1997 by Solich, Ebro, Lequeux, and Cates. And if I want to use the measure used yesterday by Daniel Fischer, I would say that that one has, as of yesterday, it has 550 citations. Let's see. And so this is known as the soft glassy rheology model. And the ingredients it has are quite simple. Each of the so basically the idea is to kind of treat all these regions of space in a mid-field manner, so to try to see how an average region of space is evolving in time. And so in this soft glassy rheology model, each region of space will have a yield energy, E, which is drawn which is a random variable drawn from a distribution which is an exponential distribution. And so for those of you who are familiar with the literature in glasses, they will already recognize that this is related to the Bouchot trap model. So every region of space has a stiffness K, some elastic stiffness, which is just a constant, same for all regions. And it has a strain variable, which is called L, and which increases with time according to some loading rate gamma dot. And the
So
idea...
This E is something which is fixed, or it's going to be changed with time?
It's going to be changed. I haven't finished my...
Okay, this is a snapshot this at one time.
That's at one
Right,
time.
right.
And then you have a yield rate, tau, that depends on E and L, and which is so tau minus 1, the yield rate, is E to the minus 1 over some x times E minus 1/2 of k L squared, which is just telling you, so maybe there is a tau 0 minus 1 here, which is just telling you that you assume that you have an Arrhenius rule for yielding given by this energy diminished by the elastic energy that has been stored by the strain. So the more you deform, the more you lower the barrier. And you have one parameter here, which will not be changing in time, which will be just a parameter of the model, which will be described as the noise temperature. And when last...
What's the exponent there in the yield energy distribution? What's the...
Here?
Yeah, inside the exponent, what is divided by to make it dimensionless?
Oh, E.
What scale?
I was just lazy, but it's just...
And what sets that?
Well, the only relevant question is actually, I mean, this is why, what is the ratio of E0 to X?
Yeah.
Right?
Right.
And so if you force me to do that, then X will have a dimension as well,
right.
and the parameter will be X divided by E0. Okay.
Thanks.
And so now the rule is that the system will yield with this rate, and when you yield, you get a new energy, E, which is drawn from the same distribution here, and you get a strain L equal to 0. So the equation for the model is an equation for the distribution function P of E, L, and T. Okay. And the evolution is very simple. It's just that the derivative with respect to time is minus gamma dot dP dl. So this is just telling you that the strain is increasing with time according to the loaded rate gamma dot. Then you have a yielding term P. And then you have a gain term, which is just at the origin. So the origin delta E equal L equal to 0, rho of E, is receiving new contributions with a rate gamma of T, which is just the sum over all E and L of P of E, L, T, divided by tau of E and L. So this is a relatively simple linear Fokker-Planck-like equation. Okay. It's completely linear here. And so this can be solved, and in the limit where the strain rate is 0, it reduces to the Bouchot trap model. So gamma dot equal to 0. The Bouchot trap model. And it has a glass transition at x equal to 1. So, or x equal to E0. And so in the driven case, what you find is that you have a Newtonian fluid. So the stress now, if you want to get the flow curve, you just come to the stress as the stiffness times the average value of the strain. Okay? And the average value of the strain you get from the distribution here. So if x now is larger than 1, you get a Newtonian fluid. So sigma is proportional to gamma dot. And if x smaller than 1, you get a yield stress fluid. With an exponent in the power law here, which is minus 1 minus x. So that's an answer to whether there are some theories predicting this exponent. So this theory would predict that you have an exponent that depends on this parameter x, which is, in a sense, a material property. It's not at all fixed by anything microscopic. I mean, it's fixed probably by the microscopic aspect, but it's something that you have to take in your model.
There is more to say about that, but don't.
Yes, I agree.
Don't stop.
The trap model basically has an exponential distribution of barriers for getting out of something, and then with exponential with Boltzmann factor. Right?
Yes.
That's what you mean by trap model?
Yes, exactly. Exactly. And so this gives you a fat tail in the distribution of escape times.
Right.
That's what. So what are the? So I will not go into the details of this model, which has been studied at length and used to reproduce or to rationalize many experimental results. But what can be said? I mean, there is one strength, which is the fact that the model, in the absence of driving, is a rather complex one, and so it has features such as aging, and you can kind of use this model to simulate relatively complex histories. Like, for example, you strain the system for a while, you stop straining, you look at it aging, you strain again, etc. And so this is the model is sufficiently complex because it has this feature that comes from the Bouchot trap model in the absence of driving, that it can reproduce rather complex histories in terms of strain. The weakness...
But it's all mean field, so there's no spatial transfer.
So it's all mean field.
Can we put those in?
So indeed, it's totally mean field.
He promised us to tell us about 3 mean field models.
So it's a completely mean field model. That's one weakness, but there are ways around that possibly, at least to make it space dependent, maybe not non-mean field, but at least to put space into the picture. But the main weakness is where does this x come from? Okay. And so the original idea of Solich, etc., was that x was coming from the noise. So remember that this is supposed to be representative of one given region in space. Okay? And then this region in space is experiencing the driving from the outside, that's the gamma dot term, but it's also experiencing all these stress redistribution that are coming from the other regions that are yielding. So the original idea of Cates, etc., was to say, well, this is like thermal noise. And so we don't know exactly what the intensity of this noise is. We will take it as a parameter. Maybe we should take this parameter as being a function of gamma dot. This would make the model more complicated and nonlinear. But in the end, it's like thermal noise. And this assumption is quite a strong one. This is the one that comes into the fact that you use Arrhenius weight here. And this is also, I believe, a weakness that you do not really know where this x comes from or how to compute it for a given model.
I do have to interrupt you. The Solich and Cates wrote a big paper a few years ago pointing out that their x indeed, if you applied thermodynamic principles, x has to be the effective temperature that Bookbinder identified.
But is that a definition of effective temperature, or that?
No, it's with our definition of
okay.
Thermodynamic definition of effective temperature, and this, in fact, answers some of your questions, but raises more.
But the question it does not answer, and which I believe is key in this model, is the fact that you use this x as an activation.
Yeah.
Because I mean, that's like Daniel was saying. I mean, the key to the model is two things: you have this activation,
I think
and you have the.
to your model, which is not going to do the same thing. So
But if I said that, for example, if I was vaguely thinking of something granular-like, and I said there's some Dietrich-Arena-like friction laws, which have creep in them and so on, and then you get creep which accelerates, and then you get reset with some other position and so on, won't that give somewhat similar features, or is it give you something very different?
Well, I come to that. I think it's different, but maybe I mean I think it's still an open
different in
question.
detail, but isn't it's going to have some similar?
Okay, we'll see. So now let me come to the second mean field model that has been proposed in the same spirit. And this is just two of the authors of the previous one, Ebro and Blöcke. So this is a PRL 98. It has 71 citations. So apparently, I'm not sure what you would conclude of that.
No, my metric was 1 over the number of citations.
It's more polite.
No, but it's what exponent you should use depends on the field, right? There are some fields with
Okay, so in this paper, Ebro make assumptions that are simple. Each region of space has a yield stress sigma y. So instead of the strain, they take as a variable, they take the stress in the region. And each region of space has a yield stress sigma y, which is always the same. I mean, which is the same for all regions. There is no random component to it. The stress sigma increases linearly until yield. That's under the loading. So sigma is linearly with time. So sigma is something like G, or dt sigma is something like the loading rate times a modulus. And again, this modulus is not a variable. It's something which is the same for all regions. And in addition to that, they claim that there is a stress diffusion term due to the yield of other regions. So let me just write the equation, because it's actually simpler to write the equations than to say it in words. So now we have a distribution function which is just for the local stress as a function of time. And this distribution function is evolving according to the systematic loading at the first term here. Then there is what I call a stress diffusion term. So there is some diffusion constant, d sigma here. And this is just telling you, in addition to the systematic loading, there is some external stress that is forcing the local stress to make some kind of random walk. Okay. And then you have a yield term. So the yield term is minus okay. So this is just telling you that if you are above yield stress, you will be yielding at a rate which is fixed, which is tau. So let's say tau is quite large. So when you exceed the yield stress, you just lose your contribution here. But in principle, you have to integrate that. So it will be sigma prime. And now there is a gain term, which is again at sigma equal to 0, which is just something which I will describe as gamma of t delta of sigma. And gamma of t is just the contribution of all the sites that are yielding. So it's just this integral here, sigma y p. Okay. So this is the total plastic activity that is feeding in sites that have a zero stress. And this is the loss term, and that's the diffusion term. Okay. So if I would just write that, this would again be a very simple linear equations, and it would not do anything interesting. The extra hypothesis which will give rise to an interesting behavior, is the fact that they assume here that this stress diffusion is due to the yield activity. And this is quantified by assuming that d sigma is alpha, which is now some material parameter times gamma of t. So you see that this makes the equation nonlinear, okay, because you have gamma which depends on p, and so d depends on p. So the coefficient in front here depends on p.
Jean-Luc, can I ask you a question?
Sure.
In general, when you think of a diffusion coefficient, you can rationalize it in terms of a Kubo approach that could tell you also whether the assumption you're making about it are consistent with basic laws or not. In this case, can one proceed similarly by finding some correlation function? In other words, if I ask you, I give you a structure,
yeah,
which you know everything from simulation, say, like yours, for example, could you evaluate that D using some Kubo approach and test possibly?
Kubo, or Einstein approach. I mean, you could just look at the mean square displacement of the fluctuation of the stress, or the mean square displacement of the stress as a function of time, subtract the drift term from here, and then get something that is like diffusion coefficient. And this is what Kirsten has been trying to do recently. It's not obvious because you have noise here, in fact. But in principle, yes, you can. Okay, and then the result. So even if the equation is nonlinear, it's actually relatively easy to solve in the stationary state, because in the stationary state, you can just say that this is a constant, and so the equation becomes, in fact, piecewise just a simple differential equation. And so what you find in the stationary state is that if alpha is larger than 1/2, then you again have a Newtonian fluid. If alpha is equal to 1/2, you have a bizarre power law dependency, which is that sigma is gamma dot to 1/5. And if alpha is smaller than 1/2, sigma is some dynamical yield stress plus something which behaves as gamma to the 1/2. And so you find again this gamma to the 1/2. So now the parameter is fixed, and this law is quite robust over a reasonably large range of gamma.
So this is the steady state.
That's the steady state, yes. So the steady state is the part that's easy to solve. It's much more difficult to solve the model for complex strain rates history. But you see that the model is really, it has kind of the same physical ingredients that the previous one, but the way the noise is treated is very different. You treat the noise as giving rise to this diffusion process rather than to activation.
I was a bit lost. Where did the alpha parameter come from?
It's just like the X parameter in SGR. You have to take it as being a material property. Okay, and then let's say you take a given flow curve. Of course, the alpha parameter will enter here and here. And so if you take a given flow curve, you may try to fit it and this would give you the alpha parameter.
So where does that parameter come in
from the other equation.
Oh, here.
Okay.
Sorry. So this is the proportionality constant. This is what gives you the strength of the diffusion if you know the strength of the plastic activity.
So we can think of it as the transfer of load from the site that yielded to the rest of the material.
Yes.
And only some of it's transferred, and that's a fraction alpha?
I'm sorry?
Only some of the load is transferred, and that's the fraction alpha? No, I guess not.
No, I guess that it's a bit more complicated than that. I mean, to me, you really have to take it as a parameter.
It works also for alpha equal to 0?
I'm sorry?
Alpha equal to 0, it works also? Because alpha smaller than 1/2.
What's alpha equal to 0 doing? That's a good question. It's not. I mean, alpha equal to 0. It's just a stupid equation, alpha equal to 0. So you don't have any.
But you have the just goes to sigma c over 2. You essentially destroy the diffusion, and what you have is the average between the maximum yield stress you have locally. So the gamma dot 1/2 will disappear, and then you will just have the yield stress, which goes to sigma c.
So basically, alpha equal to 0, you just load, yield, load, yield, load, yield. It's not very.
Are there any evidence to support this postulation? Yeah.
Well, again, this is something that Kirsten has been working on recently using simulation, trying to extract the different parameters and to see whether they were consistent with this description. And this works roughly. And then I would say in general, no, except I will now try to give you some kind of a derivation of this model from a more local model.
Can you associate the alpha to the shear modulus?
No, alpha here is a dimensionless parameter, I guess. So it's or it's maybe I mean the shear.
Alpha 0 would be in the gas state, right?
Sorry.
Alpha 0 would be then the gas state, or more, where the liquid is.
No. It's in fact that's something I do not understand very clearly. If I take this kind of thing, I would expect that alpha is a coupling parameter. That when you make the coupling stronger, you get into the jammed phase.
Yeah.
But this is not what is happening. It's actually small values of alpha that give you a yield stress. That's something I don't understand very well. But I would say the part of the model that is, I think, meaningful is really the value. You want to describe a yield stress fluid, and so you should really only consider the values of alpha that give you a yield stress fluid. The part that is Newtonian, I think the model is irrelevant. Okay. And alpha equal to 0, as we said, it's just a stupid.
And what exponents of gamma dot on the right?
1/2.
It's 1/2.
Yeah.
And above also 1/2.
And this was 1/5.
Ah, 1/5.
Okay, so now let me try to give you the version of this model, which is actually So this model is still mean field. Okay, it's just there is no space in it. So let me now try to describe the non-local version. And this is called the fluidity model. And this was in a paper by Bokeh, Ajdari, and Collin, which is also in PRL 2009. But I haven't checked the number of citations. So the non-local version goes as follows. You now look at the same, so you have the same rules in each region, but now you say, I want to consider not the average distribution, but the distribution on one site. So I is a site. Okay. So now there is space implicitly here. And so the evolution for this distribution is the same, minus gamma dot G pi, derivative with respect to sigma pi. you have the same yield term, so minus
the first term on the right-hand side is derivative with respect to time?
Time.
The right-hand side, so
it's sigma.
Sigma.
Okay, so this is just telling you that you are increasing
What
the...
was in your original equation? What is the...
Sorry, it was also sigma. Okay, so you have the yield term, the part of the yield term that goes to 0. So that's now the local plastic activity. And then what is suggested here is to say, let's do things, we want to consider things in space. So let's do things like add something which we will call like a collision term. In the sense of the Boltzmann equation, this collision term is telling you what will be the contribution of the activity of other sites on the evolution of this site.
Sorry, gamma is just the cumulative P, is that?
Gamma is, yes, gamma
It's the same
here
one,
is,
right.
so is
It's
the same
over the
here.
left.
So
Okay,
gamma
integral.
I
It's the
is
integral.
the part
The cumulative distribution.
cumulated above yield.
Yeah.
Okay. P.
But this equation is the same as the previous one with d equals 0.
It's the same as the previous one with d equal to 0, but with a what I will describe as a collision term.
The integral must be, the integral variable must be sigma.
Sigma
Not
prime,
not
sorry.
not time.
Yes. Sorry. Okay. And now the collision term will just be assumed to be a sum over all sites that are different from I of the plastic activity at this site times what the stress that is being transferred through the collision. So what I am calling collision here is just an event that is taking place at J and that is giving stress in the same way that the collision would be giving momentum in the Boltzmann equation. So Pi of sigma minus delta sigma and T. And delta sigma will be the stress transferred in the collision minus, plus here. Pi of sigma and T. And now the next step is just to say that the
delta sigma is going to depend on the distance between I and J or something?
Yeah, exactly. So it's almost the same equation that you were writing yesterday for the epidemic. Okay, so delta sigma will be, so let's assume that a collision is an event in which the site J releases completely the stress from sigma y. So delta sigma will be something like Gij sigma y, where Gij is just the Echelon propagator. So it's this cosine 4 theta divided by
I'm going to say cube.
Okay, so
Ri minus Rj to the D.
Yes. Okay, so now the last step is to do an expansion of this in terms of delta sigma. So assume that the collisions in the sense are small. And so if you do that, so you expand this, and you get something which will be some term that will be correcting here the local strain rate, okay, which will be a sum over j of pi ij, etc. Okay, so this will correct the local strain rate. And the second order will be di times the diffusion with respect to the stress, where now we have an expression for the stress diffusion coefficient, which is just the sum over j of jij, maybe one, put the 1/2 here, so 1/2 here, jij squared times sigma y squared times gamma j of t. So we now have a local stress diffusion coefficient, and you can go one step further, which is to make kind of a hydrodynamic approximation, so expand this for a plastic activity that is changing slowly in space. So now let's say that I replace I by R, okay? So the site is now becoming a region in space, and this would give me, if I make a long wavelength approximation here, would give me d of R is alpha gamma of R plus some coefficient which they call M times the Laplacian applied to gamma. So in the limit where everything is uniform in space, you recover exactly the previous Hebreu-Leuke model. When you have a stress or a strain rate that is changing in space, then the plastic activity is also changing in space, and you have a Laplacian term here. Okay? And this, in the end, so this is telling you that d minus alpha gamma is some function of space, which is the Laplacian of gamma. You know how to solve the model when d is equal to alpha gamma. And the flow curve that I wrote previously, so in the case of a uniform flow, one has d is equal to alpha gamma.
D of R is positive, or?
Sorry?
D of R is positive?
G?
Of R, no.
D should be positive, yes.
What is guaranteed?
So, is there a guarantee that D?
Some of it's squared, some of it's squared.
I mean, alpha is positive, M is positive, but I'm not sure. I mean, in the cases where people have computed solution of that, everything remains nice and positive. Yes, this one is positive, that's for sure.
But there's a second order piece coming in. The first one averages out on angles, the linear, so it's the second order one that is dominating. That's the
Well, the first order one comes into a correction to the local strain rate. Oh, sorry. Here?
Yeah. The first order one somehow, because the average over angles.
So the first one, the first order is gamma, okay? And the second order. Oh, why I don't have a gradient term here?
No. I'm thinking in powers of G. So the G, the first order term in G averages out because of the angles.
Yes.
And so you're saying it's the fluctuations in that, or the second order term in that is what's giving you this quantity. Is that?
I'm not sure which step you're talking about.
Why Gij squared?
Yes, Gij squared.
Why?
Because I expand here to second order.
Because the first order term vanishes because of angles.
No, the first order term is coming as a correction to the local strain rate. The first order is here,
But I guess I'm confused. If you, why doesn't it just average out from the angle, averaging over angles?
From theta.
From theta. Why is there a first order term?
Well, because it's multiplied by a local it would average to 0 in a homogeneous flow. I agree with you. But it's multiplied by gamma j, which may be not. So there may be, okay, there may be in a flow that is not homogeneous, there may be a local correction here.
Yeah. But the local correction sort of in some sense also of order, in some sense of also of order g squared, right? I mean the
yes,
in some loose sense. Okay, maybe. Yeah.
So for uniform flow d equal alpha gamma, one can show that the stress is proportional to gamma times gamma dot, I guess. Okay. And one finds that d minus alpha gamma is sigma minus the dynamical yield stress times gamma dot, times gamma to the 1/2 plus something which is gamma to the 3/2. And so, of course, in homogeneous flow, d is equal to alpha gamma. So this part vanishes. And so what you get, what I have written here, is nothing but the flow curve that I had before, which is sigma d plus gamma dot to the 1/2. But now, if you are under a flow that is not homogeneous, then d minus alpha gamma doesn't vanish. It's equal to this quantity. And then you get, for the plastic activity, you get a non-local diffusion equation, which looks like this. This is Laplacian here, m gamma to the 1/2 plus gamma to 3/2. And for those of you who were at the conference, this is the equation that Ken Cameron, that Cameron and co-workers are using to fit basically all the flow profiles that they get in granular mean. So I guess there was a question of where the fact that you have a length that is 1 over sigma minus sigma d square root comes from, and it's just from this equation here. Yes, well, that's not me, that was okay. Okay, so these are the mean field models. And so now what I would like to finish with is just by showing you very briefly how one can go beyond that. Okay, so these are the 3 papers here. Oh, and so then maybe that's more important than even showing you results. What is the deep difference between the SGR model and the Hebrew-Leuke model? And this maybe Elizabeth will say more about that, but what we believe now is that the Hebrew-Leuke, so if you picture your sheared domain as something that has a kind of a bistable potential energy landscape, so the thermal noise is just adding a random force here. Mechanical noise, as described by the Hebrew-Leuke model, is adding a tilt to the potential energy landscape, and the tilt itself is following a random walk. Okay, and this is very different because, for example, the escape time that you will get from the well here will be very different if you ask the question, what is the escape time with a random force? And this will be Arrhenius, that's the Kramer's problem. If you ask the question, what will be the escape time, if I add a tilt that itself is a random walk, then the answer will be a first passage time question in the flat energy landscape, and this will give you a power law in terms of barrier height. So that's a very different description, in fact, and we believe that for a thermal system, low temperatures, the description in terms of a mechanical noise that is more like a tilt that is added to this bistable system is more accurate.
So you don't need temperature at all, you're saying, it's just the mechanical noise?
Yes, so the description of mechanical noise in terms of temperature is just, I believe, not right for this type.
So if I go back to the Eshelby, now I understand what the word means. So basically, you're getting kicks in different directions, which are random because of the cosine 4 theta, basically. So you're getting some things increase, some things decrease, and so effectively that's looking like a diffusion, but when it gets to a certain, all you care is about it in one direction, and so when it gets there you go over. And so that is acting like a mechanical noise from the yield, the failures at different points, the mean field effect of that.
Yeah, right.
Okay.
At least if this type of simplified one-dimensional...
But that seems to me a much more general statement, right? That I can treat the kicks from things, from other regions as being randomly positive and negative, which they have to be because of the overall symmetry of it, right? And then the sort of second order thing is what's dominating, but I have to get to a boundary in one direction. And so it seems a rather general description that I don't need a picture exactly like that. I just need to say there's some stress at which things locally or yield, and then I build up to that by random positive and negative shifts.
Okay, so, well, just maybe...
10 minutes.
10 minutes, okay. So let me just very briefly show you what comes out from now making a detailed simulation of such an elastoplastic model. So we are not only interested in the mean field aspect, but in really reproducing some details of an experiment. And this experiment is the one that is quoted here. So basically it's a micro-emulsion of silicon oil in water, and it's a quasi 2D experiment, so that the flow curve that I already showed before, and people, I mean, the Goyon, Collin, and Bocquet did confocal microscopy and tracking of the droplets here to reconstruct the flow field in a layer of the system. So in terms of simulation, we essentially implement what I described before. Okay, so we have sites on the lattice, so this is space. We have an external driving. Each site has a stress, and we have this redistribution and yield terms. So we do it in slightly more detail than discussed here. We have a stress that is really that really has two components. We have some convection implemented. I don't go into the details. But the first thing is really to fit the model, the parameters of the model, and this we do on the macroscopic flow curve. Okay, so the macroscopic flow curve is what I showed you, and we tune the various parameters of the models, including the rules for yielding, in order to reproduce the macroscopic flow curve. And this essentially constrains the degrees of freedom of the model, the stochastic rules. And then there is one more parameter, which is the question that was asked before, which will be what is the size of the zone, the size of the site. So we set up the thing to reproduce the Poiseuille flow. So we have a stress across the channel that is linear, and with a gradient of given by the gradient, the pressure gradient. And as the stress, I mean, for this kind of system, the stress always vanishes in the middle of the channel. So as you have a yield stress fluid, there's no stress in the middle, so you have plug flow. So in the middle, the thing is not flowing at all, it's just moving in a solid-like manner. Okay, so that's how we set up the thing. So these are the velocity profiles where you see this plug flow in the middle of the channel. So this is for different widths of the channel. But the most interesting thing is that what we were able to reproduce in this kind of model is not only the flow profile here, but also the fact that if you look in detail at the physical modeling that I've been presenting, the implication is that you should see some plastic activity even in the part of the system that are not flowing. And so you will have no macroscopic strain rate in the parts of the system that are not flowing, but you will see strain fluctuations. And this is what is computed here and compared to experiments. And you see that except for the smaller channel in which the agreement is not so good, we are indeed able to capture with the model the fact that you have strain rate fluctuations in the part that is not flowing.
Can I ask you, what are the boundary conditions at the plates?
The boundary conditions here are no slip for us. So we modified the HLB propagator to have no slip boundary conditions.
And I'm sorry, generally the solid lines are the solutions to the mean field model and the processor, the lattice model?
No, the solid lines are the calculations with the elastoplastic model, so not mean field, and the crosses are the experiments.
Oh, okay.
Okay.
So what the boundary, it's a 0 and 1. The plates are 0.
Yes, by construction it's 0.
And the model doesn't have that information about the correct boundary condition, presumably that's why it's not doing what it should be doing, of course?
Yes, I will come to the boundary conditions later.
But I'm sorry, but then the curves on the left, there's something where you're solving the mean field, no? The cyan. Here we have three things. We have there's mean field data.
The experiments, which are the crosses.
Yeah.
We have the dots, which are the simulation data, the simulation of full elastoplastic. And then I think the dashed line here is just a guide. Okay. But now, so we haven't. So there's another interesting point here, which is that the fact that you have a non-local equation for the fluidity implies that in a constrained system like that, in a confined system like that, you wouldn't expect deviations from the local flow curve. Okay, and this is what was reported. So the flow curve, if you look at, let's say, the local stress as a function of the local strain, because you have this contribution, you will not exactly reproduce the local flow curve.
F is like an inverse of the local viscosity or something.
Yes.
Yeah, okay.
And indeed, you have, so if you assume that the flow curve is the macroscopic flow curve, you would get the black lines. If you take into account these non-local effects, you get in the calculations the blue line, and in the crosses are the experiment. So you have small deviations from the local flow curve that are best seen, in fact, in the vicinity of the plug here. And coming now to the bound, so let me skip that. But coming now to your question about boundary conditions, we believe, in fact, that they are quite important because in the first experiments that were reported in this type of geometry, when people inverted the flow profile to get the flow curves, they found very large deviation from the macroscopic flow curve, which is here. Okay. But this is not always the case, and in fact, it turns out that these deviations are very strong when you have rough walls, while where you have smooth walls, they are much weaker. And we believe, and we were able to more or less reproduce that again with the mesoscopic model, that this is really a boundary condition effect, that because you have two ingredients, your emulsion, when it is flowing, is actually slipping past the wall, and when the wall is rough, this induces bumps which generate extra mechanical noise. And this causes large deviation from the local flow curve. And so what we did in order to try to mimic that is to actually...
The bumps are bigger than the particle sizes or comparable?
Comparable. I mean, basically the walls are roughened with sand.
Yeah.
and so the particles are 1 micron. So, but it's a bit difficult to control this kind of thing. I mean, controlling the slip and the roughness and everything. So basically, you take what you have. And,
well, or you can just glue a layer of the stuff on the walls. Material.
These are droplets. You cannot really glue them.
I guess that's right.
Is it possible, especially if the rate of flow is increased, you may generate eddies at the boundary?
Well, maybe in an extruder geometry, but not in a quasi geometry. But these are really low Reynolds standards.
But you could considerably push it and that insists into the wrong sort of turbulent behavior.
I would be surprised, but okay. Okay, so basically the message is that we can actually reproduce this deviation from the local flow curve, but this really necessitates to introduce a specific rheology at the wall. But I will probably stop here. Sorry, I was a bit long.
Can I talk for just a minute? I'm really pleased by seeing this because it answers a whole bunch of questions. But I thought I ought to just make a few remarks to clarify what the distinction between this is and what my colleagues and I have been trying to do in what is going to be known as the SDZ field. And it's not so different. In particular, the emphasis that has appeared for the arguments about more noisy, higher temperature, higher strain rate situations, that is a lot of the driving is called mechanical driving. We even call it gamma. The thing that I am still concerned about in what John Reed's doing and what the original things, and these are topics that we've discussed for many years with Kate's Consolidation Company, is at what point do you make your local assumptions, your cells, you make some phenomenological assumptions. You introduce a plastic relaxation time there, which I have always thought was the essence of what we were trying to get out rather than put in. And so, but don't misunderstand me. What I'm seeing here is that by putting it in the way you've done, you put a whole lot of the pieces together. You especially, as far as I'm concerned, are beginning to explain this distinction between the quasi-static motions that occur when you're driving very slowly and without thermal activation, and what goes on later. But there's some real important puzzles that I would like to press you on, but not so much in public. Okay.
Yes, I think I completely agree with the question of how you cross from the kind of high temperature picture in which you have many events, and you can do a coarse-grained description that includes many events, to the picture at low temperature, very slow strain rate, where you have almost isolated events that interact.
Much more correct.
Yeah.
At the low temperature, small strain rates, what you're seeing is larger correlations. If you go back 15 years to the paper that Mike Falk and I wrote, it shows simulations that have those correlations. It in fact has a guess about how we might get the square root law, which I'm now intrigued about to think about some more. But these are all issues that have been important, and I think are very important. There are other questions that I think maybe you are addressing here better. The SGR does not do well in understanding the aging effects, or understanding, especially if they have to identify their X with a thermodynamic effect of temperature, then how does the energy or the entropy flow during aging? And I think those are pretty deep questions that still have not been answered.
But I don't agree with you. I mean, this kind of simple model does not have a decent aging. It does not have aging.
It does not have aging.
While SGR, one of the strengths of SGR is that it's complex enough that it has aging and complex rheology, and you can.
No, I'm saying something slightly different. Is that when Solich and Case tried to put it in this more thermodynamic way, it didn't quite work. Read the paper, it's not okay. But the question is, can we put your kind of model, which makes some very important improvements, into a thermodynamic framework that could explain where the energy comes from and where it goes during, for example, aging process. I'm very pleased.
Would aging rumination also need the memory term, something like that, in your stress field?
I don't know. I don't know how to put how to.
No, but what you need for the memory stuff is you have to look at the state variables and understand how they are carrying the memory and to what extent they lose the memory as they decay. And so that becomes a dynamical kind of question, a very important one.
I think you probably need to introduce more internal variables to get aging.
Yes, exactly right.
Is it possible to get strain localization with that?
Strain localization?
Sure.
Yes. I mean, in this type of fluidity models, yes, it's possible to have coexistence with
You said that this is low Reynolds numbers, and I think what parameters control exactly that Reynolds number in the setup? And if I give you complete freedom to play with elastic constant or play with the viscosities, what would the high Reynolds number limit correspond to? This may be a crazy question, but for example, let's assume that you can make the elastic constant become very large or very small. I would imagine that if they're very small, for example, things will flow much more easily.
Yes.
So do you know how to write down the Reynolds number as a function of the parameters that you're...
Well, I mean, the Reynolds number...
The elastic parameter.
I would just use the usual definition of the velocity times the viscosity, which is sigma divided by gamma dot, divided by the width of the channel, for example.
But the velocity presumably set by something that
the
depends on the
velocity.
elasticity of
yes,
your medium.
So I
don't
don't know what the exact numbers are, but I'm sure that if you, I can check it with the paper, but I'm almost sure that if you put in the numbers from the experiment and you use the
I'm sure. What I'm asking is that if you can express V in terms of actually the parameters of your model, the viscoelastic parameters, then you can also see which regime you have to go in order to go to high Reynolds number without checking actually the experiment.
Well, I think you have to go to it wouldn't really correspond to any physical situation, but we can discuss that.
Okay. So why don't we wrap it up here? We'll get lunch and we'll come back around 12. Well, as soon as you get lunch, 12:20. If you want to participate in the discussion led by Elizabeth.
That will be on a volume by the way, if you have questions on the model. This is all the version of the volume.
Okay, let's thank Jean-Louis.